Okay, guys, we have kind of a longish video for today, and this is going to cover the next assignment, and um, this is going to cover assignment 3 and into assignment 4 to some degree. We're starting with rotational kinetic energy, and to introduce kinetic energy, we're going to review linear kinetic for just a little bit. Then we'll introduce moment of inertia, which is sort of a mystery right now. Then we'll get into the moment of inertia for extended bodies, and then the parallel axis theorem is what we're going to cover. So let's review here for a sec. For linear kinetic energy, we're going to have our crate, of course, on wheels. Crate of mass m is going to experience a force, and this is going to travel a distance x. Well, we know that from our definition of, well, here's our force, applied force. We know from our definition of work that work equals the force times the displacement over which we do this work. And we can extend this, it's our mass times the acceleration of our object times that displacement. Well, we also know that from one of our kinematic equations, we can take this delta x over here, and we remember that v squared, that our velocity squared equals our initial velocity squared plus 2 times our acceleration times our change in displacement. And what we're looking for is a way to relate our velocity to how fast are we going to be going after we do all of this work, because we're going to be exerting a force and accelerating it over this distance. And it turns out that we can, if we separate the mass over here and we just look at this a delta x, okay, we can solve this equation over here for a delta x. And to do that, we're going to subtract the v naught over v squared minus v naught squared, okay, equals 2a delta x, and we divide by 2. And lo and behold, our a delta x, okay, our acceleration times our displacement, equals this v squared minus v naught squared over 2. Well, we can then plug that value into our a delta x here, and that's going to equal, okay, we move the 1/2 out front, our mass times our velocity squared minus our initial velocity squared. And this winds up being 1/2 mv squared minus 1/2 mv naught squared. And we have defined our kinetic energy to be, this would be a kinetic final, and this would be an initial kinetic energy. And this winds up being delta k as our kinetic energy. So we know that our work, okay, winds up being our change in our kinetic energy. Now, from here, we've determined that our kinetic energy, our linear kinetic energy, is 1/2 mv squared. But from yesterday's lecture, we know that v in rotational is equal to r omega. And we can then plug this, this r omega into where this v is, and then we get our version of our rotational kinetic energy. And that's going to be 1/2 mass r squared omega squared. Now what we're going to do with this, in fact, I want to erase those parentheses, and I put them around the wrong spot, because we're going to pay attention to this part right here, because we have come up with another analogous equation for our kinetic energy. And if our 1/2 matches our 1/2, and our velocity corresponds with our angular velocity here, then we have this term right here that winds up being our analogy to our mass. And we'll get into this a little bit more in a minute. So I don't know if you guys remember playing tetherball, or if you've seen tetherball before. You know, I haven't seen it on elementary playgrounds in quite some time, and it's sad because it was kind of a fun game, although I was terrible at it. I had a natural advantage because you kind of want to be taller up, because if you hit it harder and you get the angle right, then the ball spins around, and you can keep it away from the other guy. But the idea was to wrap the ball around the pole, and so essentially you have this pole, and from the top of the pole you have this ball that's swinging around. And so if you have this, let's come around this big circle like this, okay, and you'd want to hit it tangentially, because if you hit it off the tangent, then it would swing into the pole, or it would go away from you into the pole, and the trajectory would change. So you really wanted to hit it right on the tangent to get it going as fast as you could. It would be the most efficient way of doing this. Well, we know that this velocity that you would hit this with is going to equal the r, okay, times the omega that it's going to be spinning with, because velocity equals r omega. All right, well, this is sort of what we're going to be doing. It's sort of what we're going to be doing. Now imagine you have a top vision of this. So here's your pole, and you have a whole bunch of balls around the pole. So here's one, and here's one out here. Call this M1, M2, and here's one M3, and out here is M4 and M5, and all of these have their own radii to that ball. Well, let's find the kinetic energy for this system then. So if we find the kinetic energy for this system, we're going to have our K is going to equal the sum of the kinetic energies for each one, as long as they're rotating around the same point. Now this is an assumption that we have to make, that all of them almost rotate the same. They all have to rotate around the same point. But what happens here is we get the sum from I equals 1 to 5 of the individual kinetic energies of each of these balls. Well, what's this going to equal? This is going to equal it's going to equal 1/2 m1 r1 squared omega squared. And now if they're all rotating together. So here's the thing. Here's the next catch, is that these should all be rotating with each other. Okay, so this would be m1 omega 1 squared, and this would be 1/2 m2 r2 squared omega 2 squared plus ... and through the magic of ... then we get to and if we had a certain number of certain number of particles rotating around the point, we're going to have through 1/2 mn rn omega rn squared omega n squared, and that's for an infinite number of particles. Well, you guys know where that's coming. Okay, where this is going to, because this winds up being our, we're going to come back up here, this winds up being our kinetic energy, okay, and we're going to sum the whole thing. This becomes 1/2 of the sum of the r squared I mi, but the thing that they all have in common, the thing that all these things have in common down here, is if they're all rotating at the same rate, then omega is the same for all of them. So we come up here, and this becomes omega squared, but all of these are what are changing, and the 1/2 and the omega are not. And this right here is called, well, your book is going to be called the moment of inertia. But I don't want you, it's sort of it's an esoteric term that you guys don't necessarily need to be thinking about, although this is what is going to be called on your test. So you do need to know that it's called a moment of inertia. But what I want you to think, how I want you to think about this is the rotational mass of something. And because another word for mass, because if the more mass something has, the more difficult it is to move. And so that property of something that makes it difficult to move or difficult to change its motion is inertia. So we can also call this rotational inertia. You may hear me mention from time to time something of something called institutional inertia, and that is how difficult it is to get an institution like, say, a school to change about something like, say, its dress code. For example, you guys can all wear shorts now year-round, but how long did it take for Clovis Unified to do that? You haven't been able to wear shorts. I mean, when I was a student here at this school when shorts were allowed for the first time. Okay, they allowed them in, when the temperature was above 90 degrees in the paper. When the bee predicted that it was going to be 90 degrees in the paper, then the administration knew to look out, because it was going to be okay for kids to show their bare legs. Now, mind you, this was like 1987, in which case the fashion for shorts was fairly short, and to above the knee, like maybe 6 inches above the knee, for both men and women. So you get the the really tight short shorts that I'm sure there's pictures of me of those around somewhere. But that's okay. I've got great legs, so it doesn't matter. Yeah. So this is our moment of inertia, and it winds up being that a moment of inertia for a system of particles is equal to the sum of the individual moments of inertia for each one. Okay, but I'm sure you guys know where this is coming. Now, we call this I, which means that our kinetic energy is going to equal 1/2, from up here, is going to be 1/2 I omega squared. And this looks a lot closer to K equals 1/2 mv squared, where that I is our analog to mass and omega is our analog to velocity. Okay, so we have this new analogous variable, and it is the rotational mass, or the rotational inertia is how they're related. Now, as I said, you guys know where this is going, because you see these sums in here, and whenever you see a sum, you know that there's an integral coming. So we need to learn how to calculate the moment of inertia for extended bodies. All right, because you can take, you can take our particle here, and I'm actually looking for the particle that I had here the other day, and I seem to have misplaced it. So we have our I for extended bodies, and so we're going to draw our blob. Okay, and here is a little portion of mass of this blob, and we're going to call this dm, and it is at a position r. Okay, well, for this particular, and we know that our moment of inertia equals the sum of mi r squared I. I just flip them around. Well, this is going to lead to then, because summations always do, this is going to lead to I equaling the integral of r squared dm. Okay, now this only works, integral of r squared dm only works for highly symmetrical mass distributions. This will work for hoops or spheres or things with uniform density that have a very definite function to them, that have a very symmetrical a function to their shape. But this is the basis behind it. This is basically it. So I'm going to give you guys a couple of examples here on how we do this. All right, so the first one we're going to do is example. Let's pull this on here. Is example 10.5 on page 303. Now this is a pretty trivial example, but it is going to illustrate what we're talking about. We're given a hoop. Okay, we have a hoop of mass m, okay, and radius r. Okay, we want to find the rotational inertia of this. Okay, and we're going to solve it. Well, I equals integral of r squared dm. Please don't think that writing this down is a trivial thing. Just writing this down, what we have right here, will probably get you a couple of points on the exam. And if you're struggling between a 3 and a 4, or not passing and passing, or those 2 points could be, they're significant. Every point on the free response is a significant point and is an accomplishment that you should be proud of. So make sure that you're scrounging for those points by showing your work carefully and showing all of your work. Well, we're going to take this. What is going to be the dm? Well, dm is going to be this itty bitty little segment of the hoop right here. And for this particular piece right here, this dm, because the radius is the same for all of our little dm's, then our radius squared is a constant. And so this is going to equal r squared dm, with r being a constant, so we can rewrite this as r squared integral of dm. Now, our dm, we can go through the process of it. The dm is going to be, there's going to be a linear what am I say? No, but because dm is not dependent upon where it is on the hoop, and just the integral of dm is just going to equal r squared m for the mass of it. And so for any particular hoop, okay, we get an I equals m r squared, and this happens to be the maximum possible this is the maximum possible moment of inertia. You can't get more than the mass at a particular radius, because if your radius is, some parts are further away and some parts are nearer, then you start dealing a fraction of your maximum radius. But this winds up being, this is the simplistic version of a hoop. But we have another one that we're going to go over, and this one's going to, so it's a new one, and we have a uniform rod. This is exercise 10.6 on page 303, and we have a new given. Our given here is, we have a uniform rod of mass m and length L, and it spins about its center of mass. So we're going to create our axis here, and we almost always want to put our origin at the axis of rotation. It just makes the no, this should be a thin rod. I made it thicker than it needed to be. It just makes the math so much easier to do that. Okay, so this whole thing has a mass m, The whole thing is length L, and our dm looks like that. Okay, there's our dm. We want to find I, okay, and we're going to solve. Okay, so I equals integral of r squared dm. Well, this time it's a little different because we're on the x-axis, and so we're going to have an integral of x squared, because that's the distance we're going to have. But dm becomes tricky because our dm is our I is going to be dependent upon where our dm is along the axis. That the moment of inertia for this dm is not the same as the moment of inertia for this dm. And so we do need to find what dm equals in terms of x. Well, this is a relatively linear thing. It doesn't adjust to it doesn't curve. It doesn't change as we go across the entire, as we go across the entire piece here. So we can create our dm, okay, or we can find our lambda, which is our linear density of this, which is going to be our total mass divided by the length of our thing here. And so dm is, because it's our mass, so our incremental mass, our differential mass of this is going to be our density times dx is going to equal our differential mass. All right, so that means that our integral down here is going to be integral of x squared, okay, times m over L dx now. And this is what we're going to integrate. However, we are going to integrate this over what? Well, we have a beginning x and a finishing x, so where are those going to be? Well, if this whole length is L, what's this place going to be right here? And what's this place going to be right here? Well, this one's going to wind up being L over 2 negative, and this is going to be L over 2 positive, because they're both on either side of the origin. And so we're going to integrate this. I'm going to slide up to the top over here. Okay, we're going to integrate this. Our moment of inertia is going to equal the integral of negative L over 2 to L over 2 x squared m over L dx. We can pull the m over L out front. Okay, and that's going to give us equals m over L, and we integrate this x cubed, it's going to be x to the third divided by 3, x cubed over 3 from negative L over 2 to positive L over 2. Okay, and that winds up being m over L times L over 2 cubed is going to be L cubed over 8. Okay, in fact, we can pull the 3 out also, so we're going to put a 3 over here. We're going to pull this 3 out and move it to 3 over m over 3L. This is going to be L cubed over 8. And then what's negative L over 2 cubed? Well, it's going to be, we're going to have a minus, okay, a negative L cubed over 8 again. Well, that winds up being plus, so we get an equals m over 3L times L cubed. Well, 1/8 plus 1/8 is 1/4. And we can continue simplifying, so the L is going to cancel. We're going to get mL squared over 12. And so the moment of inertia of a thin rod, okay, so we come back over here. All right, the moment of inertia of our, of our uniform rod of uniform mass and length L is going to equal 1/12 mL squared, the mass of the rod times the length squared. And that will be our rotational mass for this object as it spins. Okay. Now, you may be asking yourself, well, what if it's not spinning in the center of mass? What if it's spinning somewhere else? And so we're going to have, and I'm just going to tell you what happens with it. This is called the parallel axis. This is the parallel axis theorem. And once we find what our moment of inertia is for something rotating around its center of mass, okay, we can find its moment of inertia anywhere else. And we're going to get, our moment of inertia is going to equal the I of the center of mass plus the mass of the object times the distance squared from the center of mass. All right, so let's take our rod, and instead of this is the center of mass of the rod. Okay, it's right there. But instead of rotating through this axis like we did in the previous problem, we're actually rotating through this axis over here, okay, which is the end of it. Well, this distance is L/2 for this rod. So what is our center of mass going to be? It's going to equal, well, whatever our ICM was to begin with, which was 1/12 mL squared, plus the mass of the object times the distance that the axis moved from the center of mass, which is going to be L/2 squared. Well, that becomes 1/12 mL squared plus mL squared 1/4 mL squared, and this winds up being 1/3 mL squared, and that's your parallel axis theorem. Now, it is possible, okay, now we could have done this, done the integral from, instead of doing this, we could have found this rotation just rotating from here. We could have done that. We would have just integrated, instead of integrating from negative L/2 to L/2, we would have integrated from 0 to L, and that actually would have wound up being 1/3 mL squared. And you can go back and check that if you want, but that is what the answer would have been. And in fact, you can take a look at this on page, I need to find this here. Okay, on page 303, I believe. Nope, 304, the next page. And I'm going to zoom out. All right, and here we have our moments of inertia, and somebody was already gracious enough to figure them out for you. I'm not going to have you do that, although there is, you may need to do, a cylindrical shell or hoop or something like that. It's important to know, I'm not going to have you do them. You might have a couple to do in your homework, but you're not going to see them on the test. They'll be given to you. And on my test, I will give you the moment of inertia, and on the AP test, they'll either give you the moment of inertia of the solid object, or it'll be a system of individual particles that you'll just do the sum of each individual thing, and that'll work for you. So that is the parallel axis theorem. And I wish it would just keep that color. I like the goldenrod color. That flashes every once in a while. But that's the parallel axis theorem, and the next thing we're going to cover today is going to be torque. And actually, we're not going to cover that on this particular lecture, so this should be enough to get you guys through your next assignment and introduce your moment of inertia. So we'll see you guys next time.